Yeah, welcome. Well, thank you for registering for this elective course. I'm really pleased to see this outstanding number of curious people who are looking for scientific discoveries. It is probably more than ever in previous years. And before we start dealing with the course, let me give an announcement that we may need additional meetings which were not in the registration thing. So first, I really want to learn your names, but I will not be able to do it in one day. But by the end of semester, I will memorize all names for sure. Hello, welcome. The course is project oriented, so there are many students at the beginning of the career who learn how to be a good student, how to read books, do homeworks, and pass exams. But it is a little bit different story when someone is in the research or industrial career, when it is goal achieving activity. And I think since you are in the graduate school, you are already in this mindset. So yes, you cannot. Yeah. You will try to be louder. Is it better? or I can walk closer. Okay, so and I cannot speak louder. Hope that microphone will help. So the course is based on goal achieving approach, and yes. Oh, thank you so much. Okay. And maybe you have practiced similar approach to in other classes. Instead of doing exams and homeworks, main thing we'll be doing with a research project, and upon success it can be eventually converted into peer review paper. I do not promise to everyone, but about 30% of people who previously taken the course converted their in-class project into the papers. The Wednesday evening lab is the main part of the course, and since you have registered, it means maybe I can connect it to the mask and really loud. Is it okay? Okay. So the Wednesday evening meetings will be basically computer labs. You are welcome to use the equipment here, and I'll show how to be efficient with it, but we will not use any pre-installed software from here. If you prefer to do things on your personal laptops, it could be more efficient. Consider bringing your laptops and so that you create working environment on them, and then you will be independent of the classroom. In addition to the practical things, so you will get basic skills for computational characterization of materials, and then apply the skills towards projects that basically you will choose based on your mind and heart, and maybe view of your hello, welcome, that's okay, and the opinion of your primary research advisor. In addition to this, we need some theoretical background, which is fairly secondary. So with this background or without, one can succeed in the course. But to have the course rounded up, typically it needs additional 2 lectures. This course was offered for several years, and these lectures are on YouTube. so one can watch them independently, and I will share the notes. But for those who really want to interactively go through background material, we need to select maybe a couple of hours during the week when everyone can do it. And we will follow majority. If there will be like 10 people can specific time and 5 cannot, we'll still do it, and then the rest will watch it on YouTube, because it is mostly important when we come together during the lab. So I did create a doodle poll, and please fill it and send me. I'll process your votes and opinions. Personally, for myself, best time would be like Tuesday and Friday at 11 a.m. But I know that graduate and undergraduate students are most busy people in the world, and maybe you are already booked for this time. So if the options that I submitted to Doodle poll do not match, just send me an email, and we'll try to find a balance so that those who want to discuss theoretical background will have this opportunity. So when we meet next time, I'll probably distribute some formal syllabus if you need it for your records, but we can discuss everything in person and get general idea. So the properties of materials that we can characterize range in quite broad range. And I know that more than half of this year attendees are from engineering or bioengineering. So traditional computational chemistry deals with molecules which are not very big, like 10, 30, maybe 100 atoms. The physics or computational physics people call it electronic structure theory. They deal with infinitely sized periodic models, which has some repeating patterns of atoms, and they have some specific properties like semiconductors, metals, and in the engineering, one needs interfaces between different types of materials, and because of mismatch between lattices, one may need bigger models. And the hardest headache for any computation is biorelated materials, when long and irregular biopolymers take like thousands and millions of atoms. Traditional computational chemistry characterization of small molecules is the easiest, but as needed, we will try to expand our skills to a bigger models. And as we go through the course, I will make some sort of personal interview, learning what is interesting as a major research objective for each of the class attendees. Okay. How the major activities will be organized? What is most important? So we do plan to have about 4 presentations. So the course is for about 4 months, and maybe after 3 weeks or once per month, there will be a day when everyone will present. When in the past, when the attendance of the class was lower, it was each class attendee was presenting for like 5 minutes. Right now, this opportunity can be limited, and maybe we will team up in groups of 2, so that each team has chance to present. And the 4 presentations, so once per month, will be arranged approximately in the following way. So first presentation, when we will share with each other skills in operating Linux, operating supercomputer clusters, and drawing molecular models. So some of you, based on your view to take this class, I presume that some of you already do it on daily basis, like clicking on the screen, creating molecular models, rotating them. But it would be great if we all are on the same page. And during the time before this presentation, I will try to show as much as I can, and then we chop the skills on little pieces, and then class attendees will present it to each other like mutual teaching, and then everyone will be on the same page. So second presentation will be running so-called Gaussian software, which some of you are already experts in, and some of you may not use. So this is the best software used by traditional chemists. If you are synthetic chemist, or you took chemistry and think about mixing solvents with different reactants and predicting outcome of the chemistry, this software is very user-friendly. It has very precise methods in predicting their properties, and if your professional life interacts with chemists, you will be speaking on their language. But so same about 3 weeks getting skills and then sharing between each other. There are ways directly in this software to deal with bigger models which are of broader interest, but we need to form the foundations. Then the third meeting will be based again on sharing skills of so-called VASP, Vienna Initial Simulation Package software, which is, well, we cannot cover all pieces of software. There is about 100, but it is different end. And this piece of software will be, it is designed to predict processes like melting, condensation, evaporation, periodic structures, molecular dynamics at the ab initio level when electrons are treated quantum mechanical and bonds can break and form. It's a bit hard for me to appeal to your personal experience, but I guess that maybe 2, 3, 4 people in the audience already do force field molecular mechanics, if especially in civil and environmental engineering, and there the methods, computational methods based on this force field molecular mechanics are perfect. They're ideal if the chemical identity of the objects you are dealing with is not maintained. But as soon as there are chemical transformations, breaking and formation of new bonds, one needs to use a little more expensive methods, a little smaller models, but one can predict additional class of processes. And it will be our third month and third presentation. This piece of software, VASP, is universal in everything, except it is limited with number of atoms. Like it starts challenging human patience if one needs more than 1,000 atoms. So those of you who are interested in models that can be described with 1,000 atoms are in chocolate. They will do wonders. Those who really need big models will find way to match their needs. And at the end, like maybe last day of the class or the day of exam, we will do a mini conference when everyone will present their mini research achievements, or each team. So by about like month and a half before the end of semester, we'll stop learning new skills and try applying them to research problem of your choice. And by the end of semester, you will convert your findings in form of a little mock paper, like written report of, I don't know, 3, 4, 5 pages. And at the very last day, doing the presentation in the same style as people are doing on true research conferences, which some of you may have already experienced. And then I hope you will keep friendship and good grades after the course. And some of you who are really persistent will later use this work as seeds for peer review publications if you will be interested and have steam to complete it. So it is basically an overview of what is going on. And to succeed in this activity, this when the lab is kind of sufficient. But if you want a better background, we need like this meeting plus 2 lectures, which I will select and will deliver to those who are busy or have schedule conflicts. I'll suggest just glance over lecture notes and the YouTube recordings. Okay, so I have more ideas what can be discussed today, but let me walk through the class and offer you to speak into the microphone if you have any questions or comments about the class. And maybe if you do not have any questions, just introduce yourself.
Hello everyone. I don't have any question. Okay. So myself, Hanuman Gaikwad. I am a PhD student from Materials and Nanotechnology program. I am working under Dr. Dinesh Katti. He's from Civil Engineering Department, and right now I am working in computational modeling of biomicromolecules.
Thank you much.
Hello everyone, my name is Payman. I'm a PhD student in the Civil Engineering Department. I have a question about, because right now I'm working on EIS data for cement samples. Mm-hmm. I'm curious if I'm able to define any numerical model using this quantum computation for EIS data or electrochemical models.
I do not know what is I state.
EIS.
What is it?
Electrochemical impedances spectroscopy.
Okay, I will answer as much as I can and then go to the next. So we were not talking about specific properties that we will be covering, but the materials that we are studying, they have chemical reactivity, they have mechanical properties, and they have optical properties, and they have electronic properties like conductivity or developing of potential at the interface of materials, which is the background for all electronics, for the diodes. And as soon as the structure, molecular structure of a model is known, there are ways to extract electronic and optical properties of basically any material. And I think this is related to your question. On the language of more professional chemists, it will be electrochemistry setup when one explores like oxidation reduction potentials. On the language of surface chemists, it will relate to STM experiment when one makes tunneling current across the sample and gets. And for the designing materials for electronics, it will be like predicting IV curve for a diode. So it's all related and it is very possible. The main challenge that we need to learn how to address during the first like 3 weeks or a month, how to create a model, how to convert your understanding of the material of your interest into set of atomic coordinates. So, and it can be done by several ways. One can steal it from databases which are published worldwide. One can draw them by hand. There are very nice and visually appealing tools. And one can extract or convert information from X-ray single crystal diffractometry into atomic coordinates. So if the model, if the material is crystallizable, if it is not very amorphous, there are ways, experimental ways, to do X-ray crystallography and extract positions of each atom. And then it is fed into computational chemistry software to extract the electronic structure information. In some sense, the activity in this course can be explained and referred to as exploration of structure to property relations. So we need to learn how to get structures somewhere or how to create them. And during this course, we will learn how to characterize them, how to obtain some observables based on the structure. There is an alternative method to do similar job, which we will not touch in this course at all. There are data science and machine learning, where one makes specialized programs to learn and do operations similar to interpolation. Based on a large amount of data sets, one extracts the trends and predicts properties in similar materials. We are not doing this. We will do first principles, where background information about how electrons form clouds, form eigenstates, define all properties of materials. So in some sense, from point of view of fundamental science, it is applied quantum mechanics, what we will be doing. Yeah, Payman, does it answer your question to some extent? Okay, yeah, thank you.
Hello, everyone. My name is Wenjian Nie, a first-year PhD student of civil engineering, and my advisor is Dr. Wenjie Xia. My research project now is about polymer and clay nanocomposite. And nice to meet you.
Okay, thank you very much. I know some little information about this clay project, and it is really a good thing to study. Congratulations on interesting thing.
My name's Adam. I'm in my last semester of undergrad here, and I do research in green chemistry with the parent group.
Okay. Yeah. Adam.
Hello, everyone. My name is Amir, and I'm a master's student in biomedical engineering. Currently, I'm working at a computational chemistry lab, and I'm focusing on using machine learning techniques to build computational models on different databases. And we mostly use the high performance cluster here to build our models. So that's generally what I'm focusing on.
Yeah, thank you, Amir. I don't know, maybe I can learn from you more than you can learn from me.
This is Umar Aslam. I'm a graduate student in environmental and conservation sciences. Currently, I'm working on the interactions of microplastics in the riverine ecosystems, where I would try to apply some computational techniques. And my supervisor is Dr. Chintia Vesbra.
Okay. Yeah, thank you. Thank you for the introduction. I look forward.
Hi, I'm Maya, and I'm a PhD student in electrical and computer science engineering. And I'm working with Dr. Shifang Zhang. My research work will be about microelectronic devices.
Okay.
And my one question is
I'm not planning to put any materials into the Blackboard. I will just share materials by email. So do not expect, do not try to see things there.
Hello, my name is Asya Khanum. I am from Coatings and Polymer Department. My advisor is Dr. Bukhtiar Rasulev, and my work is to develop a computational model for polymer coating materials.
Yeah. Thank you much for the introduction.
Hello, everyone. My name is Sarah Tolpa. I'm a PhD student who's Dr. Wanjishia. Mainly, I'm working on using ab initio methods and record dynamic for studying polymers and periodic structure like MOFs. So I have a running question. Will I be able during the course to develop skills to do high throughput calculations using DFT for periodic structures, which is a little bit challenging for me?
Mm-hmm. Yeah, Sarah, thank you for the question. Absolutely, yes. So the methods that we will learn in the class will be applicable to systems like MOFs without any change. So you are like a primary client who will benefit class material naturally. So most of published computational works on metal organic frameworks are done with VASP software.
So VASP is a little bit challenging with high throughput calculations for MOFs because it's very big, large, very big unit cell, right? So the computation cost is high, and also preparing the pseudo potential files for every simulation. Like, I don't know if I would be able to learn skills or tools, especially if I'm gonna do this for my project for this course. So will that be applicable, or should I think from now in something else? So I need to do high throughput calculations.
High throughput?
Yeah.
Yes. Well, there will be some challenges, of course, but there is nothing better than VASP software for MOFs. If one looks for ab initio calculations, especially if they're used for sensors, if there are some optical electronic properties, if they're used for catalysis and there is adsorption of gases, which they're often used for. Huh? It there are ways to do bigger models, and we are going to use not desktops but computer clusters, high performance clusters, and the software that we will be using is parallelizable, so one splits the job onto multiple CPUs, and it cannot get infinitely high productivity, but it is sufficient to get a lot of MOVs. So the project that you are offering is cool. It is how to say, popular and publishable, but there were other people who were trying to do ab initio calculations, and this piece of software looks very promising and usable for it.
Supercell. This is my problem. I won't be able to work on unit cell of MOF. So I will be having supercell and then do some simulation using MD simulation. And one of the outputs, I want to deep the analysis using DFT method. So VASP, when I think of, I have some experience with VASP, so all the time it's very computationally expensive for me. Like to get very accurate results, I have to wait a lot to get one simulation done.
Yes, we all will need to practice some patience. Waiting is a standard thing. No, there is no alternative. There are some really modern approaches that promise alternatives, but they often fails. And if you want just to explore yourself, there is a so-called DFTB. If you find software that it is about 10 times more productive than regular DFT, but it is also 10 times less reliable. But I really thank you for the discussion. We have dedicated attendees of the class.
Hi everyone, my name is On Rizvi. I am a graduate student and my major is materials and nanotechnology. This is my first semester, and I am working with Dr. Zhang on low temperature fuel cells and sodium ion batteries. Yeah, thank you.
Yeah, thank you.
Hello everyone, myself Dr. Debasis Golui. I came here as a Fulbright visiting scholar from India. So I am working with Dr. Achinta in environmental engineering department, and my work is on synthesis of novel nano zero valent iron for remediation of arsenic in groundwater. Thank you.
Yeah. Thank you for joining, and congratulations on your Fulbright fellowship, which is let's give an applause, because it is a rare distinction. And it's really, I'm proud that people of this caliber are attending this course.
Hello everyone, I am Anand Gupta and I am here for my PhD in the Environmental and Conservation Science Department, and my supervisor Dr. Achinte Bej-Barua, and I am basically working on cellulose nanofibers for the remediation of some pollutants from water and drinking water and the wastewater. And I am planning to functionalize that cellulose nanofibers. For that, I opted this course. I suppose this course will help me in my research. Yeah, thank you.
Thank you much for introduction.
Hello, my name is Haley Woods. I'm a chemistry PhD student in the Dr. Kalina lab.
Do you have an idea on your research project?
Yes, I will be working on modeling photosensitizers for photodynamic therapy.
Okay. Would it be metal-organic complexes? Okay. So for your small molecules, it is the same nature as what Sarah Toby is doing, but her project is multiple metals connected. It's like super big metal-organic complex, but for similar, sometimes for similar applications and some similar properties. Just you're lucky to have a smaller object for modeling.
I'm Hadassah Griffin. I'm a first-year doctoral student in the physics program. I'm planning on working with Dr. Krajewski in the summer.
Oh, okay. Do you know which class of materials or which problems are you going to solve?
I'm not too sure yet, since I'm taking this class to learn some of the software I will be using.
Okay. Yeah. Thank you for joining.
Hello everyone, my name is Amara Arshad. I am graduate student in civil engineering and my supervisor is Dr. Venjay Shah, and I'm working on the MD modeling of graphene-based nanocomposite.
Okay, yeah, thank you. And let's check if we have anyone online. Lola, would you like to introduce yourself or ask any questions, or both?
My name is Lola. I'm in the Department of Chemistry with Dr. Kalina Group, and I'm working on photophysics of metal organic complexes.
Okay, yeah, thank you much. I don't know if everyone heard, but so it's metal organic complexes as well. Yeah, thank you, Lola. So when I will return, when we will be done, I will look through your votes about the time for the lectures. And since we are already here, the main part of our meeting is done. But since semester goes by so quickly, I'll offer a little bit of theoretical background, which will be not practical skills, but things that are behind calculations. And from time to time, I may offer a little bit of short homeworks, but they are not key deciding factor. If there will be homeworks, they will be mostly for me to following and understanding if the material is well accepted. So do not panic, do not worry. It's only the way of communications. And I will try to overview some background materials to my best. Feel free to stop me, to interrupt, because we are not in academic class in a sense to get so much knowledge and pass exam. It's better if we get less knowledge, but we all are in mutual understanding and we agree on things behind. So by talking to you, I really enjoyed this little introduction, and I especially enjoyed interaction with Sarai. If everyone continues discussing the same way of the background theories, there is a chance to have great progress. Okay, so it's just we did the same style doodle poll last year. There is no mandatory book. The thing that we will go over here interactively is much better and more valuable. But there are a couple of recommended books. Neither one of the book guarantees success. They can be much deeper than anything I can tell here, but they are going too far in depth in one or another direction. We need combination of several skills and several ideas. So if you really have nothing to do rather than read scientific books, you're welcome to check them out or purchase and learn, and it will create a helpful background. But no guarantee. It's only auxiliary. Here is an approximate tentative list of the lectures. So what I would like to deliver apart from the labs. So amount of the labs is basically amount of the weeks until the end of semester. So like 4 weeks per month, about 16, 15 labs, and about twice per week lecture. So there will be 4 chapters, one with fundamentals about the how to think and how to, well, all this background materials deal with converting ideas into language of mathematical formulas, which later on is converted into language of programming for doing calculations. And I know that some of you can be curious about mathematical derivations, especially if you are from physics, and some of you could be interested only in practical applications. So the course is already designed. I cannot change much, but if the derivations looks boring, just tolerate it and wait until we go to more practical things. And any questions are very welcome. So there will be an attempt to convert some easy ideas in maybe not so easy equations, because it is what we need to get general idea how the codes are working. And if you plan to include part of the research that we will do here into your thesis or peer review paper, you need to go over barrier of reviewers. And reviewers in some sub-communities are very picky about methodology. So if one uses equations, or at least write words behind these equations, it is much easier to overcome the process of reviewing. So it basically provides motivation for suffering of 30 lectures of formulas. So the first chapter will deal with the way how one can mathematically treat nuclear degrees of freedom, which means interatomic distances, and electronic degrees of freedom, which means like positions of electrons and shapes of electronic clouds. And it explains, this chapter will deal with the fact that it is almost impossible to treat them simultaneously. One needs to solve equations or solve computational equations related to positions of atoms and shapes of electronic clouds independently. So it's enough. The simple idea is enough for like 6-7 lectures. And in parallel, we will work on building models and then do presentations. Then the second chapter will be about so-called Hartree-Fock theory, which is useless. It is not used by any modern researchers, but it is present in all textbooks because it is the only theory that can be conveyed in a short way, which is logically consistent. So the amount of approximations is limited, and all procedures that later on are implemented in computation are very clear. And all electronic structure codes can be considered as improvement of this theory. So it's a fundamental idea behind any software that describes electronic properties. including not only conductivity potentials, but also optical properties. It's more philosophical scientific background. I do not believe any of us will use it for the project. The third chapter will be on, and at the end we will do presentation on Gaussian software, where Hartree-Fock theory is implemented, and many other much better theories are implemented as well. Then the third chapter, which will be like January, February, March, approximately, will be on density functional theory, which is not the most precise one, but it is, by today, it is a balance between precision and numerical cost. So Sarah may argue with this and tell that it is insufficient, it is too expensive numerically, but if one gets to something less expensive, one gets degradation in precision and reliability. So it's quite universal piece of knowledge that we should go over. In ideal case, with mathematical formula. In more optimal case, at least verbally describing what is going on and how it relates to observables. And if this would be a longer theoretical course on fundamentals of quantum chemistry, there would be like another couple of chapters on so-called multi-reference methods or many-body perturbation theory, which is a main interest of Professor Krzyzewski. These theories that he is interested in would be between here and there, and they will be skipped from course. But the fundamentals that we go over will be sufficient for you to go independently and interact with him on the efficient way. So in the last chapter will be focused on observables. One cannot do everything at once, and there will be a little bit more focus on optical related observables, such as absorption and emission spectra, like color of a material. And it is related with energies of electronic states. And as we go through, there will be another computational method called time-dependent density functional theory, which is very different from regular DFT. And at the end of third chapter, we'll do presentation on VASP software. At the end of this fourth month, we'll do reports on mini research projects, and then we will be done. So when do we want to finish today? How much energy do you have? Are you tired, angry, ready to go home, or have energy to listen for a little bit more? A little more? Okay, yeah, thank you. So here is the summary of the course. If you meet your colleagues next day, or your advisor, and someone asks you what were you doing, what the course is about, you can tell it's like computational structure to property relation. And basically what we do fits into this full box diagram. So we are getting some equations, maybe a little more than in this box, but basically they all are based on Schrödinger equations. So equations for wave functions. And they are, we learn how to build models, and then one feed in theories and models into software that runs on hardware to predict properties. And then these properties can be compared to experiment or just analyzed on their own. So it's a general funnel flow chart of the whole course, and we will try to follow it as much as possible. I hope we will meet before coming Wednesday once or twice, based on your votes for this doodle poll. But if not, and I want to offer a little homework. Again, it is very informal. I just need it. Do not worry. Even better, submit blank. It will mean that I didn't convey material good. It's not for you, more for me. So this will be based on interpreting the little material that I'm going to deliver. So it will request to this homework requests to count amount of terms in a formula. So we can close eyes and not write the formula, but just tell how many terms are in the formula for the energy. And I'm going to basically explain all information needed for this little homework in whatever we are going to be here. It can be done quite quick. Okay. So no, I think it is too funny and too boring. I'm going to skip a couple of slides and better explain it by words. It's all correct, but so thank you so much. Let me skip because it's all correct, and I would be happy to speak for hours about these things, but they're not so. It's not key things. It's secondary. Okay. So this little diagram on the left is what I would like to speak about, and it will be related to the little homework. And I will show a couple of diagrams like this in several forms, and homework relates to drawing diagram like this and counting terms. So at least one attendee of this class was in the PChem class that I was teaching, and basic PChem class, basic physical chemistry class, basic quantum mechanics classes typically deal with one electron problem, where there is a potential, like background potential of positively charged ions or some other materials, and electron that experiences moving in this potential, right? The main challenge for true description of realistic materials comes from the fact that there is almost no materials that have one electron. Typically, even single atoms have multiple, like almost 100 in radioactive elements, right? And electrons repel each other. So they behave like particles, and one have so many electrons that their motion and their eigenstates are very complicated. So basically, the whole software behind this course is developed in order to address this challenge: how electrons repel each other and settle in a material to define its properties. So here, I believe we have pink or whatever, orange 2+. It's a helium atom, right? So the nucleus has charge +2, and there are 2 electrons with -1 each. And if you want to speak about this helium atom on mathematical language, we set up position of each particle, like coordinate, set up their mutual distances, and define how the energies depend on their pairwise distances. So if there are 3 particles, there will be 3 vectors connecting them, and each of them will define potential energy, right? Is Coulomb attraction and repulsion is a natural concept for everyone, or someone needs words about it? Please vote. Like, are you happy with Coulomb, or you are unhappy with Coulomb? Do not hesitate. It's not to praise or point on someone. Just let me know if you Coulomb attraction. Everyone is happy with it. Anyone give me a secret sign, like if someone is not happy with Coulomb attraction. Okay, so everyone is happy, right? So there will be Coulombic attraction can be chopped on 2 types: the blue to blue repulsion, right, and orange to blue attraction. And people call it like electron energy and nuclei to electron energy, right? And then there will be kinetic energy for each particle. So totally for this molecule, there will be 6 terms in the total energy. So kinetic energy of each particle, 3, and then 3 terms of potential energy, total 6. Is it doable? So for helium atom is doable. Anyone wants more explanation about helium atom? Okay. And there are ways to do it in more details. And when people try to solve it by pen and paper, there are different systems of coordinates. Later on, we will use so-called atomic system of units. So when in each of us probably had this Coulombic attraction in high school or college physics, right? And there is a factor in front of Coulomb, like 1/4 pi dielectric permittivity of vacuum, right? And it's okay, but for I was hating it to put extra symbols all the time, and converting of units takes effort. So when one is speaking about electrons and nuclei, there is a specific system of units where all equations look a little shorter. So if one selects system of units where mass of electron is considered 1, charge of electron is considered 1, and Planck constant is considered 1, the Coulomb attraction doesn't need this 1/4 pi dielectric constant of vacuum, and several other terms look much simpler. Okay, so here where I want to put more details. So probably I even try to redraw this figure on the blackboard, and if you like to take notes, maybe it is the only note that you may wish to take. So try to draw this figure, follow me, and we'll do a little exercise. It's not mandatory, but recommended. So what is a molecule? I'm going to make a little interview with maybe a couple of class attendees. If anyone wants to speak up, please raise hand. If you don't, I will just approach. Sarah, is it so boring that you decided to leave, or you came closer to hear better? Okay, so what is a molecule?
Sorry?
What is a molecule? What's the definition of a molecule?
Sum of atoms bonded chemically together.
Okay, good. So it was an answer of engineer. Now we want to hear the answer of a chemist. What is a molecule?
Atoms put together into a molecule.
Okay, they're quite close, right? Like atoms put together. Let's hear an opinion of a physicist.
Chemical or elements bonded together by their electrons.
Okay, yeah, thank you. So there was one word more in the definition that came from a professional physicist. There was a focus on electrons, right? So each atom can be ionized. Electrons can be taken away from the atom, right? And electrons may or may not stay attached to its parent atom, right? So it will be more rigorous to say that a molecule is just a constellation, a combination of positively charged nuclei and negatively charged electrons, right? Make sense? And since this description is needed, it's fundamental for things that we will be doing. And if you want the, so it's origin, if you want to be specific, if you want to convert description from verbal to more mathematical things, we can, here is an attempt to speak about maybe one of the simplest or second simplest molecule, H2, molecular hydrogen. So we have two protons with positive charges, and I would use capital letters for protons, and then there are two negative electrons, and one can use lowercase symbols to have difference, to notate ions and electrons different. So my goal, and as soon as I achieve this goal, we'll be done for the day. My goal is to set up the energy of this molecule as function of position and velocity, so momenta of each ion. Because the stuff that I went over really quickly, that I didn't want to stay together, it was oversimplified summary of quantum mechanics. So basically one needs to formulate operator of total energy and formulate a wave function and find the eigenstates. I plan to speak about it more, and if you all have the slide, you can just look through them. They're correct. They're just boring for me. And the software on computers will solve all problems for us. This word is not what people are typically hearing in basic courses like PChem or quantum mechanics, but right now we need to know what is going on, but we are not going to solve problems ourselves. We just need to have the right language to understand what is going on. Therefore, I'm kind of relaxed about the equations, and I'm very tolerant how you take them. So 4 vectors, right? So our players are R1, R2, R1, R2. But in addition to the positions, we have velocities. So the temperature is typically non-zero, at least in our room, which means all particles are moving, right? So there is a velocity of each ion, and definitely electrons are never stay still. So there is some motion, and therefore we will have the either velocity or momentum P1, P2, P1, P2 is capital, or P is mass times velocity, right? Feel free to stop me anytime. If if you feel discomfort, I'm really happy to stop and discuss any basic concepts.
Can't see the bottom of the whiteboard.
Oh,
so-
okay. There is an anecdote about the leader of United States and leader of Soviet Union making discussion in like 40s about Cold War. So one of the leaders calling to each other, and people in the cabinet are listening to it and telling like, when you were answering the phone, you were telling no, no, yes, no, no. You are a hard man. You refused anything. But once you said, you answered yes. What was the question? Did you hear me well? So I was fearing when you had a question that it will be something serious, but I think Amir just wants me to write things R1, R2, R1, R2, P1, P2, P capital 1, P2 on and all our vectors on the top side of the board. Okay. So the positions are used for potential energy, momenta are used for kinetic energy, right? And the potential energy is taken not from positions themselves, but from their pairwise subtraction, right? So we connect this by arrows and tell the distance between two nuclei will be R1 minus R2, vector, vector, absolute value, right? And then the Coulombic term will be 1 over this distance, and it will be with sign plus because they have the same sign, right? The charge will be positive, proton, positive. Now for here, between two electrons, it will be R1, R2 lowercase, subtract absolute value, 1 divided by this, and it will be also positive because negative gives positive. They repel each other. And then in addition to this, we do have 1, 2, 3, and 4. 4 mutual subtractions of between positions of protons and electrons. So 1 over R1, R1. Negative because it is a positive particle and negative charge particle they attract. Minus 1 over R1, R2. Negative 1 over R2, R1. Negative 1 over R2, R2. So total number of terms for potential energy will be 1, 2, 3, 4, 5, 6. So the little homework will be asking, it will offer a little bit different molecule and ask how many terms of potential energy are there. And you can do similar diagram and just count lines. Is it doable? Okay. Now let's count terms for kinetic energy. So each ion and electron, each particle moves independently. So for kinetic energy, we will have P1 squared over mass of proton, P2 squared mass of proton, plus lowercase p1 squared of 2 mass of electron, plus p2 squared over mass of electron. So total 4. So 6 terms for potential, 4 terms for kinetic, and 10 total. So there will be similar, like a molecule with different number of electrons and nuclei, but just try to do similar thing, and by looking on how you follow it, I will develop a grade for myself if I communicated the idea as well. Okay, and these slides have the same idea. So connecting this tips of the arrows with lines and counting them in the reasonable way. So why we are wasting your valuable time on this exercise? Do we have any benefits for our major goal of characterizing properties of materials? How does this exercise relate to computers predicting like conductivity or color of a molecule? We are getting an idea that even a very small molecule have many terms. And one would need some tricks to describe them in a simplified way. And we learn that this large amount of terms in the energy can be chopped on categories. We can categorize them. And this categorization on classes, we are doing like people in plant science and zoology. They just have so many animals and they give names to them. We want to do the same categorization for terms in the Hamiltonian, in the total energy. So we can tell that even if molecule will be much bigger, we can identify kinetic energies of all ions, right? All nuclei. And we can call them T sub n, T for like translation or temperature energy. Yeah. Then we will have certain amount of terms for kinetic energy of electrons, right? There will be 2 of them. I just hate my ugly handwriting, therefore I'm hiding it. Then there will be potential energy of nuclear to nuclear or ion to ion repulsion. So here it will be only 1 term, but you have this category, ion to ion repulsion. And ion to ion interaction, which is not only repulsion if they are not ionized, atom to atom repulsion and attraction, is what is used in force field as an input. Like distances, torsion angles are either fit or extracted from ab initio and then used to predict configurations. But here we have another types of interaction. So instead of atom to atom, we tell nuclei to nuclei or ion to ion to be more rigorous. Then potential energy of electrons. Here we have also there is only 2 electrons and it's 1 term, but in bigger molecules there will be more of those. And this is the most challenging term that makes life really hard. And therefore computational chemistry exists as a standalone area of science because people compete who describe this term better and more precisely. And then there is a category with largest number of of terms is, we can call it potential N to E, nuclei to electron. So attraction between electrons and nuclei. By taking bigger molecules, we are not going to write down this Hamiltonian. We can make, if really needed, we can make a common formula with summation sign, like summation over all electrons, summation over all electrons, but it will be quite universal to tell that any molecule will have 5 types of the terms in total energy. Kinetic energy of nucleus, kinetic energy of electrons, kinetic energy of potential energy, nuclear repulsion, electron repulsion, electron nuclear attraction. So there is a serious reason to focus our attention on this fact, because the path to achieve our goals, to predict properties of materials, will deal with neglecting some of these terms or assuming they are not changing or changing quickly. So in our next meetings, we will focus attention on the fact that on one hand, reliable description of materials is not possible without quantum properties of electrons and sometimes nuclei. On the other hand, exact solution of quantum properties of a model with more than, let's say, 3 degrees of freedom is not possible at all. So one will need to sacrifice something. And basically, computational chemistry is science of sacrifice in mathematical sense, or science of approximating on neglecting terms. And yes?
We neglect the terms, so can it be means at the end, we will not get the correct result, right?
Yes, the word is not correct, but there will be controlled error, and one can not completely neglect term, but assume that it will stop depending on distances and will be a constant, or one stops feedback between different degrees of freedom. So we need some additional tricks to deal with large number of degrees of freedom. So it is not possible to solve exact quantum problem for many degrees of freedom now, and it will be not possible at least for next 10 years. Later, if quantum computers will become reality, one can expand horizons. But for next 10 years, we still need to do the approximations and survive for our profession. And this language of categorizing energy, energy terms, types of interactions inside any molecule is an important way to speak about molecules and materials. And I will try to avoid explicit writing of equations as much as possible, but I still will be keeping notations like this and explaining how methods, computational algorithms are working, referring to these different types of interaction. So this is needed. Let's see if we have more slides. Well, if one wants to be really rigorous and general, then masses of different ions can be different. And instead of explicit summation, one can put just summation sign. Masses of all electrons are the same, so there is no index here. The charges of different ions can be different, right? And if one has like mixture of nitrogens, carbons, uraniums, iron, copper, each of them has different charge number, and it should be taken into account in nuclear repulsion. For electrons, charges are the same. One needs just to count all electrons pairwise. And for electron to nuclear attraction, one also needs to take care of the charge number of each ion. In our practical approach, it will be taken care of by the software. So software that we are going to use is already written, and we just need to get general idea how it works. But it's better to be like educated user. Okay, I was about to finish. So yeah, okay, so it is the last slide. So for any molecule based on quantum theory, every property, every behavior of any object can be predicted if we know Hamiltonian operator, if we can categorize the energy based on all parameters. So we use this energy operator for Schrödinger equation and for predicting everything, right? And Hamiltonian total energy operator is composed of these 4 types of terms. And then the equations that we need to solve is just this molecular Hamiltonian acting on the molecular wave function that depends on all ions and all electrons and finding eigenstates. So such wave function that is not perturbed by acting on this operator. So linear algebra eigenstate problem. And this angular bracket symbolizes that there are several ions and several electrons. So this equation has a really large number of independent variables, even for small molecules. And it is a main motivation to design some approximations without significant loss of precision. Okay, I think it is enough for today. Many thanks for selecting this course. I hope no one will drop it after, no one will be scared of these equations. And I look forward to read your feedback about the times. If times that I offered in the Doodle poll do not work, send me an email, I can redo it. Because I want to have doors open for everyone as much as possible. So meeting is done. Everyone is welcome to disconnect or depart. I'll stay here to answer questions if any, but if you need to go, please do. Oh, do you have any questions to ask now?
No.